Kia ora koutou katoa, it's Mrs. Goodson here, and this video is about rates of reaction and how to design a science investigation of a factor that affects rate of reaction. And it's for level 1 science and a focus on chemistry. So just a reminder of the factors that affect rate of reaction. So there are 4 things that will speed up or slow down a chemical reaction, and that is the concentration of the reactants, the temperature of the system, the surface area if there's a solid reactant, and for some reactions there is a specific catalyst that can affect the rate. So first of all, when you're planning your science investigation, you want to think about the one thing that you're going to change, and we call that our independent variable. Now in this reaction here, we've got a reaction flask, a conical flask, and it contains some calcium carbonate, which is some marble chips, and some dilute hydrochloric acid solution. And when those two things combine, one is a base, the carbonate is a base, reacts with the acid, and you get an acid-base reaction. So you get a salt and water, and you get carbon dioxide because it's a carbonate. Now, what you'd expect to see is bubbles of the carbon dioxide gas being made. And so we've got the flask has got a bung here, and the carbon dioxide gas will be collected, and then we can measure in this measuring cylinder the change in this level of this water, and we can therefore measure how much product is made over time. So to change it, we could change the surface area of the limestone or the calcium carbonate chips. So we could, for example, use powdered limestone. We could change the concentration of the acid solution. We could change the temperature of the acid solution. We could put it in a water bath and heat it up, or an ice bath and cool it down. And these things are going to mean that the reaction will go faster or slower. Another reaction we could do is reacting solution A, which is actually sodium thiosulfate, a base, mixed with hydrochloric acid again when we've got that acid, which is another acid-base reaction. Now, when this reaction occurs, it's between two clear solutions. It makes a precipitate and it makes it go cloudy. So we can use that to judge the end point of the reaction from when the cross disappears. So just think about what could be changed in this reaction to change the rate. Okay, so there's no solid, so we can't change the surface area. There is two solutions, so we can change the concentration of those solutions. And there is also temperature. We could put this flask, or we could use warmed up reactants using a water bath or an ice bath to cool it down, change the temperature. There is no catalyst for this reaction. Okay, so remember, rate is what we're trying to find, but what we actually measure is time. So time is our dependent variable. Time for the cross to disappear, or time for the reactants to be used up. So the longer the time, the slower the rate. So it's the inverse. So time is long, rate is small. Okay, so and vice versa. So we're going to measure how long a reaction takes from start to end point, and we're going to do it in seconds. Seconds is units. Really important that you include the unit in your investigation. The end point depends on the setup of the experiment. It might be when one of the reactants runs out, or for example, when the cross disappears. So we're going to change just one thing, we're going to measure one thing, and we're going to keep everything else the same, and that's our controlled variables. In order for our investigation to be valid, we need to control or keep the same all the other factors that might affect the results. For rate of reaction, this includes those factors that we are not changing, for example, concentration, surface area, temperature. So we just want to change one, and the other ones we keep the same. We're not going to worry too much about catalysts, okay? To make it valid, we should carry out all our trials on the same day with the same equipment, for example, the same size and shape of the flask, and the same person using the stopwatch, because their reaction time might be different to someone else, as well as the same person judging the endpoint. The volumes we use should be kept the same, and we want to use a measuring cylinders, and we want to specify what size measuring cylinder we're going to use, and that we're going to avoid parallax error by looking at it at eye level and from the bottom of the meniscus. We want the starting point to be the same for each trial, so the flask should be cleaned before each trial to remove any solid particles. What would happen if these things were not kept the same? Can you think of anything else that should be kept the same? Okay, so just a note on parallax error. So measuring cylinders have narrow tubes with very accurate markings. So we don't use a beaker, we use a measuring cylinder. And the liquid in the narrow tube makes a semicircle called a meniscus. To get the most accurate volume, the reading should be taken at eye level from the bottom of the meniscus. So that is from this point here. And all measuring cylinders are made so that that's where you should take the reading. When we carry out an experiment in chemistry, small errors are made that are impossible to completely avoid. We call this experimental error. In order to minimize the effect of experimental error and make sure our results are reliable and trustworthy, we should repeat the experiment more than once to check we get the same result. So we do 3 trials for each independent variable value and then take the average or the mean. So this video has been about identifying the independent variable, the dependent variable, and the controlled variables for a chemistry investigation into a factor that affects rate of reaction, and also how to make sure the results are reliable.